All right, let's just dive right into this incredibly fascinating explainer where we're going to demystify the building blocks of quantum computing. If you've ever wondered how quantum computers actually process information to perform these seemingly magical, impossible calculations, you are in exactly the right place. Today, we're popping open the quantum toolbox to look at the absolute foundation of quantum algorithms, quantum gates.
Here's our roadmap for this explainer. 1. Bits versus qubits. 2. The quantum toolbox. 3. The magic of entanglement. 4. Building quantum circuits. And 5. Why quantum gates actually matter.
Section 1. Bits versus qubits, the raw material.
Okay, so the absolutely crucial thing to grasp here is that while classical bits are trapped in this rigid binary world, qubits exist in a fluid, continuous realm of possibilities. Every single device you use right now, your phone, your laptop, it all runs on classical bits. They are just like a rigid light switch, always strictly 0 or strictly 1, with billions of them flipping on and off every second. But a qubit, it does something wildly different. A qubit can be 0, 1, or a superposition of both. Think of a spinning coin. While that coin is spinning, it's not heads or tails, right? It's just this blur of both probabilities at once. It only collapses to a definite state when you catch it, or in quantum terms, when you measure it.
Now, if your brain kind of hurts trying to picture a coin landing on heads and tails simultaneously, well, you're doing it right. It is bizarre. And that's exactly why we use this 3D geometric tool called the Bloch sphere. Instead of trying to juggle complex numbers and matrices in our heads, the Bloch sphere simply maps a qubit state to a point on the surface of a sphere. So the North Pole is our classical 0, and the South Pole is our classical 1, but unlike classical bits that awkwardly jump abruptly between those two poles, qubits transition beautifully and smoothly. Every single point on the entire surface of this sphere embodies a unique quantum superposition.
Section 2. The quantum toolbox. Single qubit gates.
So let's open that toolbox. Our very first tool is the poly-X gate, which is honestly the closest thing we have to a standard classical NOT gate. If you apply the X gate to a qubit that's currently sitting at 0, it rotates it exactly 180 degrees around the X-axis of our Bloch sphere, flipping it straight to a 1. It's simple, it's fundamental, and yeah, it functions practically identically to flipping that classical light switch from off to on.
Next up, we have the poly gate. Much like the X gate, it also flips the qubit 180 degrees, but it does so around the Y-axis. Now, what makes this one super fascinating is that it introduces a mathematically quirky phase shift using the imaginary number I. And this right here is where we start seeing operations that are fundamentally completely different from anything a classical logic gate could ever dream of doing.
And then we have the poly-Z gate. This gate is uniquely quantum. There is absolutely zero classical equivalent for this. As a phase shifter, it actually doesn't flip the qubit's core probability from 0 to 1 at all. Instead, it beautifully rotates the qubit around the Z-axis, essentially multiplying its amplitude by -1 if it happens to be in the 1 state. Now, you can't actually see a phase difference if you just measure a single isolated qubit. But make no mistake, this phase shifting is profoundly important for creating the quantum interference that gives quantum algorithms their mind-blowing speed.
But honestly, the absolute rock star of the single qubit toolbox is the Hadamard gate. It literally splits our qubit into parallel worlds of equal probability. It's often so beautifully referred to as the gateway to quantum superposition. If you feed a strict, boring classical 0 or 1 into an H-gate, it grabs that qubit and places it perfectly onto the equator of the Bloch sphere. It gives it a perfectly equal 50% chance of being measured as a 0 and a 50% chance of being measured as a 1. Without the Hadamard gate, a quantum circuit would really just be an incredibly expensive, slightly probabilistic classical computer. The H-gate is literally our ticket out of the classical realm.
Section 3. The magic of entanglement. Connecting worlds.
Okay, so to connect these isolated qubits, we have to use something called a CNOT gate, which stands for controlled NOT. You can think of it as a master switch that forces interaction between two totally separate particles. It takes two inputs, a control qubit and a target qubit, and the rule here is incredibly simple but so powerful. The target qubit flips its state if, and literally only if, the control qubit is a 1. If the control qubit is a 0, the target qubit is left completely untouched. And this brilliantly illustrates how we actually create entanglement, linking two qubits so deeply that measuring one instantly dictates the fate of the other. Here's how it plays out. Step 1. We start with two qubits at 0. Step 2. We hit the first one with our star player, the Hadamard gate, throwing it right into that spinning coin superposition. Step 3, we apply the C0 gate, using that spinning coin as the control for our second qubit. Because the first qubit is in a superposition of both 0 and 1, the second qubit enters a superposition of being flipped and not flipped simultaneously. They are now locked into what physicists call a Bell state, meaning no matter how far apart you separate them in the universe, if you measure one and it collapses to a 0, the other will instantly collapse to match it. It is wild.
Section 4. Building quantum circuits, tying it all together.
So here is a quick, super handy cheat sheet mapping these abstract mathematical gates to familiar, everyday analogies. When quantum programmers design algorithms, they certainly aren't doing brutal matrix math by hand every single time. They string these logical gates together from left to right, kind of like reading a musical score. Our X gate acts as that white switch, the Z gate acts as the phase shifter, the Hadamard is our coin spinner, and the C0 acts as that multi-qubit master switch.
When quantum programmers write code, they rely on specific visual symbols, like this adorable little cross symbol which represents a swap gate, to route information through the processor. Just as the name implies, a swap gate completely exchanges the states of two qubits. This is crucial because in actual hardware, qubits are physically bolted in place on a chip. So if qubit A needs to interact with a distant qubit C, programmers use swap gates to essentially leapfrog the quantum information right across the chip to the correct physical location, all without destroying the delicate data.
Now, this is how the entanglement process we just walked through is actually written out in a professional circuit diagram. The lines represent our qubits moving forward in time from left to right. But keep in mind, inside the actual physical hardware, deep inside those giant freezing cold dilution refrigerators, this visual circuit translates into exquisitely precise microwave pulses. Those pulses literally bombard the qubits with exact timing and just extraordinary accuracy, physically rotating our probability amplitudes on the Bloch sphere exactly as the math dictates.
Section 5. Why quantum gates matter. The grand design.
So why does all this microscopic manipulation actually matter to us? Well, by combining these tiny gates into a universal gate set, we can run computations that are mathematically impossible for classical machines. Just like a classical computer only needs a few basic logic gates to run anything from a basic calculator app to a massive video game, a quantum computer only needs a small universal set of gates, like the Hadamards, phase, and C0 gates, to approximate any quantum algorithm imaginable. Plus, and this is so cool, unlike classical and or OR gates which literally destroy information when they run, all quantum gate operations are perfectly 100% reversible. No information is ever lost. By leveraging superposition and entanglement, these exact circuits are actively being developed right now to optimize global financial models, simulate ridiculously complex molecules for life-saving drugs, and unlock the next massive leaps in artificial intelligence.
It all just leaves us with a truly awe-inspiring thought about the raw power of this quantum toolbox. We're literally taking the strangest, most counterintuitive rules of the microscopic universe and taming them into a reliable computational language. If quantum gates can process parallel realities, what reality are they going to build for us next? I highly encourage you to keep exploring this fascinating microscopic world because understanding quantum gates today means understanding the bedrock of tomorrow's technology. Thanks so much for diving into this explainer with me.